Algebra 2, Lesson 5-2, page 258. It says, use a graphing calculator to graph the polynomial function. Then use the graph to determine the function's domain, range, and end behavior. So let's see here. Okay, I've got x to the 7th already graphed. And there it goes. And if you'll look, it's going to get all the way, and Control T. You can look, see the x values there, 4, 6, 10, 16, and it just keeps on going. Way down here, negative, or 88, 162, it's going to get way out there. And then it gets way to the left too, okay? Control T. All right, so we're going to say the domain is all real numbers. What about the range? The range is the y values, the outputs that it covers. And if we look at this, see, it's going to keep on going and going and going. Eventually, they get up there to positive infinity. It's going to go down here, and it's going to go all the way down to negative infinity. So we're going to say the range is all real numbers as well. Now the end behavior, as x approaches positive infinity, what does y do? Well, as x gets way out here, y gets up yonder. So f of x, or y, approaches positive infinity. What happens as x approaches negative infinity? As f of x gets out here, or as x gets out here, way out here, f of x is going to go way down. So we're going to say f of x approaches negative infinity. Okay? So we have an odd number exponent, and when we do, the end behavior goes in opposite directions. Now what about negative x to the 9th? Let's do that one there. Okay, notice how it reflected it over the x-axis, the negative did. All right. The domain will still be all real numbers, okay? Because it is going to get out here and it is going to get out there, okay? Because that's at an angle and that's at an angle. What about the range? Well, the range is going on up and it's going on down there. So it's going to be all real numbers as well. Now the end behavior has changed as x approaches positive infinity. So as x gets out here somewhere, y is going to negative infinity. F of x approaches negative infinity. As x approaches negative infinity, as x gets out here, y is getting way up there, so it's going to approach positive infinity. F of x approaches positive infinity. Well, let's try x again. We had an odd exponent, so we had legs going in the opposite direction. All right. Let's try number 3. That's x to the 10th. We got x caret 10. Notice the legs. This time they're both up. That's because we have an even exponent. If you have an even exponent, the legs will go in the same direction. All right, since a was positive, they both went up. Now what about the domain? As X is going to get way out here and way out there, okay, because that's at a slight angle. So the domain, and I'll just use D, is going to be all real numbers. And the range is going to be different this time. Look at the range. Okay, it only gets down here to 0. So we're going to say the range is y such that y is greater than or equal to 0. Now the end behavior, as x approaches positive infinity, as x gets way out here somewhere, what does y do? Well, it's way up yonder. So f of x approaches positive infinity. As x approaches negative infinity, what is y doing? As x gets way out here, y is still approaching positive infinity. F of x approaches positive infinity. Notice here, even exponent and the end behavior, they both go the same direction. Notice here, odd exponent and the end behavior, they go in opposite directions. Okay? What about negative x to the 10th? What is that negative going to do? It's going to reflect it over the x-axis. So what does that do for the domain? The domain is still all real numbers. What about the range? Well, the range only gets up here to 0. So we're going to say the domain is all real numbers, and the range is going to be y such that y is less than or equal to 0. Okay? What about the end behavior? As x approaches positive infinity, as x gets out here towards positive infinity, y gets down there towards negative infinity. F of x approaches negative infinity. As x approaches negative infinity, what does y do? Y gets out, or x gets out here, y gets way down there. So f of x approaches negative infinity. Notice, even exponent, in behavior in the same direction. Number 5, it says use a graphing calculator to graph the function. Then use the graph to determine the number of turning points and the number and type, global or local, but not global, of any maximum or minimum values. So we have x times x plus 1 times x plus 3. So we got x times x plus 1 times x plus 3. Now notice how I put the multiplication symbol between each one. I didn't mean to hit that. I meant to hit enter. There we go. When I look at this, I notice a couple of things. One, we have a turning point here, and we have a turning point there. Okay, so we got 2 turning points. And let's see here. So we got 2 turning points. Also, look, you got x plus 1 and x plus 3. Notice it crosses at x equals 0, it crosses at x equals -1, it crosses at x equals -3. So if you take those and you got x equals 0, x plus 1 equals 0, and x plus 3 equals 0, you get x equals 0, x equals -1, and x equals -3. And that's the three places that it crossed the x-axis. 0, -1, and -3. All right, so there was two turning points, and we had one local max and one local minimum. We had 1, 2, 3, 3 x's, so that is a third degree polynomial. So it can have up to 2 turning points, and in this one it had 2. Now let's look here. We got 1, 2, 3, 4. So this is going to be a fourth degree polynomial. We can have up to 3 turning points. May not have that many, but we can have up to 3. So let's graph that. And we got x plus 1 squared times x minus 1 times x minus 2, I think that's right, x minus, oh golly, let's go right here. X minus 2. Press enter, and look at there. Now what do we got this time? Okay, what do we got this time? We have 1, 2, 3 turning points. 3 turning points. And what else do we have? We have a local min. This is a local min. This is a global min. And this here is a local max. So we have one local max, we have one local min, and we have one global min. Let's go see if we can look at that. Where is that? Oh, there it is. Look at here. This is a local max. This one does not have a global max because this leg goes all the way up to positive infinity. This is a local min because this leg here keeps on going and it goes all the way down to negative infinity. So it does not have a global. It does not have a global min. Number 7. We have 3 x's, so we're going to have up to 2 turning points. Ooh. We got negative x times x minus 2, x minus 2, and then squared. And there we go. negative x. Oh, that was supposed to be times. Okay, now notice x minus 2, so if you set that equal to 0, you get x equals 2. All right, but notice since this is squared, it didn't actually go across the axis, it just went up and touched it. Okay, so we had 3 x's and we've got 3 turning points. Or excuse me, 2 turning points. We got a turning point here and a turning point there. So we have 2 turning points. And we also have 1 local max right there and 1 local min. And that's right there. One local max and 1 local min. Let's take a look at number 8 here. Okay. Again, we got the negative out there, so that's going to reflect it over the x-axis. Oh, I hate when that happens. We got negative, and then that's x minus 1 times x plus 2. And that's to the 3rd power. Now, how many x's do we have? We have 4. 4 x's. So we can have up to 3 turning points. But if you'll notice, we actually only have 1 turning point. Okay, we have 1 turning point and 1 global max. Because that is the global max, that is as high as it goes. 1 turning point and 1 global max. Excellent job, folks. Now it says sketch the polynomial function. So we have x squared times x minus 2. So let's take a look at it. What do we know? All right, we've got 3 x's, correct? 3 x's, so that's a 3rd degree polynomial. So that's going to tell us that our legs are going to go in opposite directions. A here is positive, so we know it's going to start here and it's going to end down here somewhere. Now we need to find out where it crosses the x-axis. So we got x squared equals 0. Take the square root of both sides, and we got x equals 0. So we're going to have a point at x equals 0. Also, this is squared, so it's going to touch, but it's not actually going to go beyond. We have x minus 2, set that equal to 0, so we got x equals 2. So we're going to go across at 2. So here is what our polynomial will look like. wish I was a better artist. Let me see, I can do better than that. 0. And it looks something about like that, okay? And if you like, you can graph it here on your calculator and see. All right, number 10. What do we got here? Number 10. How many x's do we have? Looks like we got 3 x's. Okay, so that's a third degree polynomial. Also, A is -1. So instead of going like this, instead of going like that, since it's negative, it's going to reflect over the x-axis. That's going to put a leg up here and a leg down there. Okay? Remember, odd, opposite directions. All right, we've got x plus 1 equals 0, so we got x equals -1. It's going to cross there. X minus 2 equals 0, so x equals 2, so it's going to cross there. And we got x minus 3 equals 0, so we got x equals 3. It's going to cross there. So we're looking at something that does about like this right here. And there we go. And there is our third degree polynomial. Not too hard, not too hard at all. Take a look at number 11. How many x's do we have this time? 1, 2, 3, 4. So that's a fourth degree. Which means both legs will be going in the same direction. Now, A out here is positive, so we're going to have a leg up here. So we got x equals 0. We got a spot there. X plus 2, x plus 2 equals 0, so x equals -2. We got a spot here at -2. And we got x minus 1 equals 0, so x equals 1. That's right there. All right. 4, so the leg's going to be up here, so we're going to have something that looks like this. It's going to go down, and since this -2 is squared, it's going to touch it, but it's not going to cross it. Go back up a little bit. It's going to go down, back up a little bit, and it should look something like this right here. Okay. Excellent deal. To create an open top box out of a sheet of cardboard that is 6 inches long and 3 inches wide, you make a square flap of side length x inches in each corner by cutting along one of the flap's sides and folding along the other. Once you fold up the 4 sides of the box, you glue each flap to the side it overlaps to the nearest tenth. Find the value of x that maximizes the volume of the box. All right, we're going to need some real estate for this. Here we go. All right, so I'm looking at, this is 6 inches total, but you got an x here and an x there, so it's going to be minus 2x. So that's that side over there. This side over here is going to be 3 minus 2x, because you got an x here and an x there, right? Okay. We're talking about, we want to find, what's the other formula? Find the volume of the box. So the V of x is going to be, volume is 3 dimensions, so you got length times width times height. Okay, so the volume of the box is going to be the length, which is 6 minus 2x times the width, which is 3 minus 2x, times just x. Okay. Now we want to find that maximizes the volume of the box. Now if you wanted to, you could multiply all this and find the factors and solve and stuff like that. There's an easier way. Let's go to our calculator. And let's see, graphs. And we have 6 minus 2x times 3 minus 2x times x. And it looks like this. Okay. That down here, that looks like a minimum. This up here looks like a maximum to me. Okay, the local max. There you go. Let's find that. Menu 6, 4. Oh, I don't know why I did it. Menu 6, 3. Okay. So our length is going to be 0.634. So x equals 0.634 inches tall, and our maximum volume is going to be 5.2. cubic inches. And there we go. All right, folks, excellent job, and we'll see you tomorrow in class.